Smoke uses maximum operating conditions supplied by vendors, and optional derating factors, to calculate the safe operating limits of a component's parameters. Smoke then compares circuit simulation results to the component's safe operating limits, and if the circuit simulation exceeds the safe operating limits, Smoke identifies the problem parameters. Maximum operating conditions are supplied by vendors as properties on the parts that you add to your schematic. Maximum operating conditions can be assigned directly to a component or as a parameter that is placed on the variable's component. For example, if we look at the properties on our R3 resistor, it has a maximum operating power condition with a value set to Rmax. Rmax is then a parameter that we will find on our variable's component, which is set to 0.25 watts. So, R3 has a maximum power dissipation of 0.25 watts, and if this is violated, smoke will indicate it. Other properties may be used in the calculation of the maximum operating conditions. For example, if we look at each transistor, it has an RCA, a case to ambient thermal resistance that uses the default value, which is then used to calculate the junction temperature of the transistor. And if the junction temperature of the transistor violates its maximum value, then smoke will indicate an error. The smoke analysis can only be run after a transient analysis, so we'll create a new simulation profile for a transient analysis by selecting PSpice, New Simulation Profile, and giving our profile a name and defining a transient analysis that runs for 2 milliseconds. We'll then run our transient simulation, and then just to verify our transient simulation, we'll add 2 traces to our trace window. First, we'll add the current through our input voltage source. Then we use the add plot to window command to add a second plot to our window and to this second plot, we'll add a trace for the power through our Q1 resistor. After the transient analysis run, we can go back to Capture and select PSpice Advanced Analysis, Smoke to start our smoke analysis. After the smoke simulation is completed, the results are displayed in the smoke window. The red rows indicate parameters that are above their maximum operating conditions. And if we right mouse button in the spreadsheet, we can see that we're viewing average values, RMS values, as well as peak values. If we toggle off the RMS values and the peak values, we are currently just looking at the average values. We're currently sorted from maximum % over the maximum operating condition in descending order, and if we look at our Q1 transistor, we can see that we are violating our maximum power dissipation by 150%, and the chart showed us our rated value, the % of derating for that value, the maximum based on that derating, and our measured value. And our measured value of 829 milliwatts is 158% above our maximum derated value. For our resistor, R1, our % maximum above our power dissipation is listed as max with no percentage. The max occurs in the % max column for a component's power dissipation max operating condition because the measured value column is being divided by the 0 from the max derating column. We also notice that for our Q1 transistor, the TJ parameter, the maximum junction temperature, is rated at 200 degrees and our measured value is 215 degrees. Which is 108% of our maximum value. Perhaps we could apply a heat sink to our Q1 device to see if we can get its junction temperature below its maximum operating condition. A heat sink on our Q1 transistor would lower the RCA parameter or the thermal resistance from the case to the ambient temperature. We'll go back to our schematic and we'll add a heat sink to both of our transistors. We'll select our two transistors, right mouse button and select Edit Properties, and for the RCA parameter, the thermal resistance from the case to the ambient temperature, we'll change that to 0.2 degrees Celsius per watt. And we'll save our schematic. We'll rerun our transient analysis, which will regenerate our netlist, and then in Smoke, we can rerun our smoke analysis. After the smoke simulation, we see that our Q1 junction temperature has been reduced from 215 degrees, which was outside of the maximum value, to 68.5 degrees, which is 35% of the maximum value. So it's indicated as green on our checks rather than the red that we had before. We also find that the maximum power through our transistor has been reduced to 104% of its maximum, just slightly over its maximum operating condition, reduced from 158% that we saw in our first simulation. Our R1 resistor was a quarter watt resistor with a maximum power dissipation of 250 milliwatts. And our measured value is almost twice that, 442 milliwatts. Let's consider using a higher powered resistor for R1. We'll go back to Capture and edit the properties on our R1 resistor. The current power for the resistor is set to a quarter watt based on the Rmax value that is on our variables component. We can override the value on the variables component by entering a value of 2 watts for the power property of our R1 resistor. We'll save our design and rerun our transient analysis. After our transient analysis is rerun, we can go back and run our smoke analysis. After we rerun the analysis, we can see that for R1, we haven't changed our measured power through the resistor. It's still 442 milliwatts, but that's now well below our maximum operating condition, which is now 2 watts since we've changed to a larger resistor. And in the graph, it's listed as green because it is only at 23% of its current maximum operating condition. Smoke used the maximum operating conditions supplied by vendors to calculate the safe operating limits of a component's parameters and compare them to our circuit simulation. Smoke then identified the problem parameters so that we could modify our design to make sure all the parameters meet operating conditions.